This video will cover the final two concepts in our unit on limits. I'm going to discuss how to evaluate limits as they approach infinity, and I'm also going to look at limits of some basic trig functions. Okay, we'll start out with limits at infinity, which is pretty quick and short to go through here. Just making sure you're familiar with some of the symbols. So hopefully you're familiar with the symbol for infinity, which is kind of like a sideways 8. Positive infinity, think of a number line, like so. Well, if you keep going this way forever, you're headed towards positive infinity. If you keep going this way in a number line, you're 0, 1, negatives are on this side, that means you're headed towards negative infinity. Make sure you understand infinity is not a number. It's a process of making numbers bigger and bigger and bigger, or smaller and smaller and smaller, depending which direction you're going. So there's no, the symbol infinity has no mathematical processes like variables and numbers do. So sometimes students say, oh, look, I've got infinity over infinity, that must equal 1. And that is not true, because these are not numbers, they're processes. All right, so make sure you realize that infinity is just the process of making numbers arbitrarily. Arbitrarily just means as big as you need them to be, or small as you need them to be to see what's happening. And we're going to look at limits of functions as the variable is getting either bigger and bigger and bigger, or smaller and smaller and smaller. And if it's getting close to some particular number, that will be your answer. Sometimes they won't be getting close to any particular number. Here's 3 visuals that hopefully will help you a little bit. So if I look at this one, if x goes to infinity, that's out here, x is approaching infinity. If I said, what is the limit of this function as x is approaching infinity, you would say, well, as x gets bigger and bigger and bigger, it appears to be getting closer and closer to this line, if it continued out here, which is the line y equals L. So our limit here would be L. However, if I checked this one and said, what's the limit of this function as x approaches negative infinity? That means as x goes this way. Well, you can see that, assuming there's an arrow on the end of this, as x goes this way and continues to go this way, this graph's just going to keep heading up here towards infinity. So it's not getting close to any specific number like this one did. This is an example where the limit would not exist. Now look at this one. The limit of this function as the x values approach infinity would be, so you can kind of see you're getting this pattern of looping back and forth, but I think you would agree that if that pattern continued, you're going to get closer and closer and closer to that pink line, which is the line y equals L, as x goes to infinity. However, if you go back this way, the limit of this function as x approaches negative infinity, this would be another example of does not exist, because it's not, if it goes this way, it's not getting close to any specific line or value on the y scale. It appears to, even if this is looping, the loops are getting bigger and bigger and bigger all the time, which means it's not getting close to any specific value. So it would be it does not exist. And the final one, same idea. So if I looked at, again, this is if x is going to infinity, what is this graph doing as the x values go to infinity? It's getting close to L on the y scale. Now here, let's assume, just to show you that you can have graphs. Let's suppose that one out that way. Well, this would be an example that if I check the other end of it, the limit of f of x as x went to negative infinity, which means this way. So as the x values, I pick x values out here and look at the graph's going to be closer and closer and closer to that line. So it also equals L on that one as well. So that would be just kind of reading them from looking at a graph if you had the graph in front of you, which of course we don't usually have. So we need to learn how to do these limits algebraically. So if I have the limit of 1 over x as x is getting really, really big. Well, this is the graph of y equals 1 over x, if that'll help you, but we can kind of reason our way through this. If I took 1 and divided it by an infinitely big number, so for example, let's say you had 1 divided by this huge, huge number. Well, without me saying exactly what the answer is, I think we would all agree and say, well, it's going to be really, 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 really small. The answer is basically going to be 0.0000 with a 1 tacked on the end. Versus here, let's say I go 1 and I divide by negative infinity, because x is going to negative infinity. That would be something like 1 over negative 9999. So it's a really, really small number. When you divide that out, you're still going to get very, very close to 0. The only difference, instead of getting positive 0.0001, you're going to get negative 0.00001. So in this case, if you have a limit of 1 over x, as x is going to plus or minus infinity, it won't matter which, you are going to always be getting closer and closer to 0. One of them's just on the positive side of 0, the other one's just on the negative side of 0, but it doesn't matter. Both scenarios are getting closer and closer to the number 0. And you can look at it and say, well, are you sure? Look at the graph. So look at this one. Here would be if x is going towards positive infinity. Well, I think you'd agree if I continue that out, it's going to get closer and closer to the line here, which is y equals 0. If I went this way, which is out toward negative infinity, this graph's going to get closer and closer to the same line, just on the bottom side of the line. That's why I got negative this example, and I got positive here. So what we want to do is generalize that and say, well, okay, that's good. What if there's an exponent down here on the x? It's not going to make any difference, really. If we just kind of use our common sense and reason our way through these, this would just be 1 over an infinitely large, now this is saying if n is a positive integer, 1 over an infinitely large number, and then you raise it to some exponent. So let's say I put it to the nth power. Well, all that's going to do is make this number on the bottom even bigger. So when you take 1 and you divide by this even bigger number, it's still going to be 0. It's not going to change a thing. So that's why it's still 0. So you can have 1 over just x, or 1 over x squared, 1 over x to the 10th. You could even have, it doesn't have to be a 1, because I could have the limit of, it could be a million if you wanted it to be, it doesn't matter, over x, and x is going to infinity. This is what they mean by arbitrarily large. Well, they say, well, how big could the bottom number be? Well, it could be as big as you want it to be. So imagine if we made this a massive, massive, massive number. I don't care about this number, because I can make the one on the bottom so much bigger than it that when I divide those out, I'm still going to get 0. So generally, the property here is written out, but this could be any number, as long as it's a member of the real numbers, it'd be fine. It'll work. Okay, so we'll come back to that scenario in a second, but I'm going to look at the first type of limits at infinity we want you to be able to evaluate, and they are involving rational functions. Rational functions is a fancy math word for fraction. Okay, so you just have to keep in mind some basic properties of fractions. If I had 12 plus 8, you'd all agree that's 20. 6 take away 2, that's 4. And the final answer, 5. Well, if I was to take and divide the numerator, every term by 2, and then as long as I do the same thing to the denominator, in theory, that should give me the same answer. Think of fractions. If I gave you the fraction 3/12, well, the way you reduce it, everyone says, oh, that's 1/4. Oh, yeah, really? Why is that? Because I divided the numerator by 3 and the denominator by 3. Well, you can't divide the numerator by something and then the denominator by something different and think that you're still going to get an equivalent fraction. You have to divide the numerator and denominator by the same thing. So here, as long as I divide the numerator, everything by 2, and then the denominator, everything by 2, it should still be equivalent to what we had here, which is 5. So let's check that. 12 divided by 2 is 6. 8 divided by 2 is 4. 6 divided by 2 is 3. 2 divided by 2 is 1, so I've got 10 over 2, which is equal to 5. Same thing I got. again, which all makes sense. That's just basic properties of fractions and numbers and equality. Well, we're going to look at rational fraction expressions where the variable is approaching plus or minus infinity. It doesn't matter which one. Now, this is really kind of overdoing it, but basically the process we're going to do is right down here. This is the important part. After you get it all expanded out, the numerator and denominator, you have to have a polynomial, which means x to positive exponents, over another polynomial, x to positive exponents. The process will be to divide the numerator and denominator by the highest power that you see anywhere in the entire rational expression. This one, when I look it over, I see x squared, x to the 1, x squared, x to the 1. The highest exponent anywhere in this whole fraction is x squared. So what we do is we divide the numerator by x squared and the denominator by x squared. 3x squared over x squared, you just get 3. X over x squared, I would get 1 over x. 2 divided by x squared is just 2 over x squared. 5x squared divided by x squared, I'd get 5. 4x over x squared, I'd get 4 over x. 1 over x squared doesn't reduce any, I have 1 over x squared. Well, then essentially what you can do is just take the limit of each of these terms individually as x is going to infinity. Now they're kind of showing that all out here. I'll show you another example that I would do. I would not show near as much work as this. But essentially what you're going to have, so the 3 is going to be there because the x squared is canceled. 1 over an infinitely large number. So we already talked about that. 1 over an infinitely large number is basically 0. 2 over an infinitely large number squared is going to be 0. 4 divided by an infinitely large number is going to be 0. And 1 divided by an infinitely large number squared is going to be 0. So these are all zeros. The only thing left is your 3 over 5. Therefore, our answer to that question will be 3 over 5. Now, students will often say, oh, that's a neat little strategy. I'm going to use that all the time. It only is useful for rational expressions where the variable is approaching infinity or negative infinity. If this is approaching 6, this isn't going to help you any. Okay, but because it's approaching infinity or negative infinity, this is a strategy that works very nicely. This is just a visual to show you. So if you were to graph y equals 3x squared, over that, which is the limit we just had to evaluate, and you looked at it as x goes to positive infinity, which is over here, you can see that it's getting close to the line right here, which is 0.6, which is 3/5. The answer we got doing it out by pencil and paper. All right, so let's try an example of that. All right, so here's one. Now, the last one was laid out even a little bit easier than this one, but the first thing you have to do, so the giveaway is x is going to infinity. I say, okay, we've only looked at, we're not going to look at very many cases of this. So I've looked at this scenario and say, okay, it's a fraction. We've done this. What we do is we expand first, always. Last one, we didn't have to do that. It was already expanded. All right. After you expand, you're going to divide by the highest power of the variable. All right, so let's go to this one and do some expanding. Limit as x goes to infinity. This is a binomial squared. Make sure you use your 3 steps and square it properly. Square the first, multiply, which it would give me negative 6x squared, but then I have to double that. So negative 12x squared. Square this one, plus 9x to the 4th. Binomial multiplied by binomial. So this multiplied by this, 6x to the 4th. This multiplied by this is negative 10x squared. 1 times this plus 3x squared. 1 times negative 5 is a minus 5. All right, so now I've got, I'm just going to clean up the denominator a little bit. The limit as x goes to infinity, 4 minus 12x squared plus 9x to the 4th. Now, planning ahead, this is what I mean by I'm not going to show nearly as much work as they did in the example I gave you from the textbook. I know I'm going to divide by the highest power of x. When I go to put my line here, I'm just going to leave some room so I can put some stuff underneath these. So there's some space here. And then I'm going to collect these two in the middle. So I've got 6x to the fourth, subtract 7x squared minus 5. I'm going to divide by the highest power of x. So you look over the whole fraction, numerator and denominator. And remember, you have to divide the numerator by the same thing as the denominator. What will happen is sometimes, I think I have an example in a minute, but let's say the highest here was a 5, and here was a 4. So students will say, oh, okay, well, the highest one is 5. But they think they divide the top by 1 and the bottom one by, let's say, a different exponent. You can't. It has to be the same exponent for everything when you divide. And it's got to be the highest one you see anywhere in the whole fraction. In this one, x to the fourth is the highest one, so we are going to divide every term by x to the fourth, like so. Now, and again, I'm not going to show all of this. They're going to cross out here and here. So you're left with a 9 there and a 6 there. All of these other terms, 4 over x to the fourth, as x gets really, really big and you raise it to the fourth power, you take 4 and divide by that, you're basically going to get 0. This one, if there's a power of x left in the denominator, which is going to be the case for every single term besides the highest powered one, this is in theory 12 over x squared, it's going to go to 0. This one is going to go to 0 because it's going to be 7 over x squared. 5 over x to the fourth is going to be 0. So our final answer here is going to equal 0 minus 0 plus 9 because they canceled out here. They also crossed out here, leaving me with a 6. And then I had 0 and 0 here, leaving me with a 9 in the numerator, 6 in the denominator. That reduces to 3 over 2 if you divide them both by 3. Okay, so that is how you approach if you've got a rational expression. The other scenario is when you're dealing with exponential functions. So functions of the form b to the x, where b is some number more than one. So let's say it's 2 to the x, 3 to the x, 5 to the x, whatever. Here's an example of what b to the x looks like in general, the graph shown down below. Well, you can see that as x goes to positive infinity, which is over this way. So if you had, for example, y equals the function 2 to the x, and I said, what's the limit of 2 to the x as x goes to infinity? Well, this could be the graph easily of 2 to the x. As x gets really, really big, this graph's going to keep heading up here and just keep getting bigger and bigger and bigger. So it's not getting close to any specific number. This would be an example of doesn't exist. However, if I did the limit of 2 to the x as x goes to negative infinity, look at your graph. So now as x moves out this way, the graph is coming down, getting closer and closer to the line down here, which is y equals 0. So this one would be a 0. Now, sometimes students will say, well, yeah, but I don't know what those graphs look like. Well, you don't have to. You just have to have some what we call number sense. If this graph was nowhere to be found and I had this, I'd be, so let's suppose you didn't have that. Here's what your brain would be saying. It wants me to take the base 2 and raise it to a really, really big exponent. Well, you think about what happens. The bigger that exponent, the bigger your answer is going to be. So your answer is just going to keep getting bigger and bigger and bigger all the time. Infinity is not a number, so the function is not getting close to any particular number. It's just getting bigger and bigger, which is why I would then say doesn't exist. Versus this one, if I do a kind of an analysis of it and say, okay, they want me to put 2 to the negative infinity. So you need to know a little bit of your exponent work and say, well, anytime I have a base and I raise it to a negative exponent, that really means 1 over 2 to the positive infinity. So you're taking 12B math, you should clearly know that 3 to the negative 2 is the same thing as 1 over 3 to the 2. And again, if you don't, that's going to contribute to issues in trying to do limits. We assume you've mastered your exponents and some basic algebra concepts at this point. So this would be the fraction 1 over 9. So if I have 2 to the negative infinity, that's 1 over 2 to the infinity. But we just said that 2 to the infinity is going to get really, really big. But in this case, it's going to be 1 over that really, really big answer. And we've discussed that and said that, well, that means we're going to get closer and closer to 0. So there's how you can get the answers using number sense without having that actual graph there to have to guide you through that. All right. Now, that's all we're going to cover with limits at infinity. Let's look at a few of them. So let's suppose I had this one. I think I got 4. Yeah, I think I got 4 of these. Okay, so if I look at, these are just exponential situations. So this time, x is going to negative infinity. So I'm taking 2 to the exponent 3 minus a negative infinity. Well, negative is going to be plus. So if you take an infinitely big number and you add 3, that's really not going to do a whole lot other than tell me that exponent is really big. So if you have the base 2 and you raise it to a really big exponent, you're just going to keep getting bigger and bigger answers, which means you're not going to be getting close to any specific number. It does not exist. This one, it's a little different here because you've got your numerator to the x, your denominator to the x. So sometimes students will say, well, 2 to an infinitely big number is infinity. 5 to an infinitely big number is also infinity. But here's what you need to think about. If your exponent was, let's say, 100, and you had 2 to the 100 over 5 to the 100, these are not the same numbers. They're both big numbers, but the one in the denominator is going to be a bigger number because the base that you're raising up here is a larger base than it is here. So if you put the same exponent on them, this one will become a bigger number. As those exponents get bigger and bigger and bigger, the gap between these two numbers is going to get bigger and bigger. And as you divide those two numbers out, you're going to get something closer and closer to 0. Well, that's easy for me to explain on a video, but that's hard for students to write a paragraph or make a video to explain that when they're trying to get the marks for the question. So what you would do in this case, or what I would do, is this. I would take here, and because they're both raised to the same exponent, I would just go 2/5 to the x. And then here's all you got to know. If you take any number smaller than 1, 0.5, for example, 0.9, anything smaller than 1, and you raise it to really, really, really big exponents. If you don't believe me, check it on your calculator. Put 0.5 to the exponent 10, then put 0.5 to the exponent 50, then put 0.5 to the exponent 100. You're going to get answers that get closer and closer to 0. Versus if you take a number that's more than 1, we've already kind of discussed this, and you raise it up to an exponent, you're going to get numbers or answers. So, for example, 2, or even 1.2 to the 10, 1.2 to the 100, 1.2 to the 1,000. You're going to just get answers that get bigger and bigger and bigger all the time. They're not getting close to any specific number. This scenario does not exist. So all you got to do is when you get to here, say, okay, I have a number smaller than 1. I'm raising it to a really big exponent. That is going to ensure that I get closer and closer to 0. So again, not a lot of work physically shown there, a lot of mathematical number sense reasoning going on up in your head. Okay, let's look at this one. So here the x is only on the exponent. So I would say I've got 3 to an infinitely big number in the numerator, and I'm going to divide it by 4. Well, this numerator is going to be such a large number, and it's going to keep getting bigger and bigger and bigger all the time. So if you have an infinitely large number and you divide it by 4, you're still just going to keep getting answers that are bigger and bigger and bigger all the time, which will be another does not exist. And over here, I've got 1 over 5. X is going to negative infinity. Now, we've already talked about negative exponents a moment ago. Again, if you're taking 12B math, you need to be able to get your brain wrapped around negative exponents. If I have 1 over x to the negative 3, you need to know that that's the same thing as x to the positive 3. Take the reciprocal, switch your exponent. This then is the same as 5 to the infinity. Well, if you take the number 5 and just keep raising it to large exponents, you're going to get an answer that just keeps getting bigger and bigger. Now, infinity cannot be an answer. It's not a number. So that just means that you're getting another scenario of does not exist. All right, so not a lot of fancy calculations going on in these exponential situations. It's more just using, hopefully, the number sense you've developed over the span of your high school math career. All right, so that was a quick run through of how to do limits as they approach positive and negative infinity. We looked at basically two scenarios: rational expressions, that's where you divide by the highest power of x, and then we did an example or a few examples of dealing with exponential situations, and that is where you hopefully use your number sense and reasoning abilities to figure those ones out. Okay, last thing in limits that I'm going to cover for you this year is going to be how to do the limits of trig functions. So you remember from 12a what our trig functions look like. This is the graph of sine x. This is the graph of cos x. If I look at sine x, this graph continues down this way, as does this one down this way. If you looked at sine of x as you approach 0, so whether you're coming from this direction or this direction, you're getting close to 0 on the y-scale. If you approach 0 from the left or the right on the cosine graph, you're getting close to 1. Right? So those are just kind of refreshing your memory on your two basic functions. Well, there's one important identity that we need students to know in order to evaluate limits of trig functions in this section that we're going to do. Again, I'm going to keep it basic, but I'm just going to show you how this identity right here actually works. So number one, you need to make sure you realize this identity that I'm showing you here is only true if you use angles in radians. Does not hold true if you started trying to check this out with 30 degrees, or sorry, 0 degrees. If you picked angles really close to 0 degrees and did this calculation out, you do not get the same thing you do if you do it in radians. So if we're in radians, here's the pic. So if you had the graph of y equals sine theta over theta, this is what it would look like. We're looking at this graph as theta gets close to 0 on this side and this side, we're getting close to the number 1. Now, I can't put 0 exactly, so why don't you just substitute 0? Well, because if you do that, the sine of 0, we just looked at the picture, it's 0, and if theta is 0, well, all of a sudden you have 0 over 0, which we've identified as being called indeterminate. But I'm showing you here, if you do a visual, as you get close to 0, I don't mean at 0, I mean just to the right of it and just to the left of it, you're getting close to the number 1 on the y scale. Here showing you typing in numbers for theta. If you put these angles in, the closer I make these angles to 0, the closer they're getting to an actual 1. At 0, notice it spits out error because you can't divide by 0. So if I actually looked at this graph, there's a hole in it right there, which I cannot see, but it's that one small spot where it would be undefined. So what we want you to know is, I'll have it in a nice box here. This is what you need to know. The limit of the sine of theta divided by some angle theta as the angle goes to 0 is always equal to 1. The fact that this equals 1, think about this. The only way you get 1 is if you take something and you divide it by itself. So if I flip that and put the bottom and the top and the numerator to the denominator, do you think it would change anything, or would you still get 1? Well, I think we'd agree it's not going to change anything. You're still going to get 1, meaning this identity will also hold true if I write it the other way. Theta over sine of theta will also equal to 1. Okay, and again, it's just because of this whole idea. The only way to get 1 is to have two things that are equivalent to each other. And if you flip that, take the reciprocal, it's still going to divide out to give you a 1. All right, so how does this work? Well, here's our first example. One thing you got to make sure you clearly understand. You cannot, I can't stress this enough, you cannot change the argument, which is the part that comes after the trig function, of any trig function. Students will get correct answers in this, doing things that are very, very mathematically wrong. So just because you get the right answer doesn't mean your rationale or your thinking is correct. So please try to keep that in mind. Never, never, very clearly, but never change an argument in a trig ratio. So this would be the argument. This would be the argument. It's on the next page, by the way. So if I look at these ones, this is the argument. This is the argument. You cannot do anything with those. I may be saying, I don't know what you mean, do anything with them. Hopefully you'll be clear of that in a second. All right, so this is what we're going to do. Now, when this pattern says the limit as theta goes to 0 of, let's say, sine of theta over theta equals 1, well, theta here is generic, meaning it's the argument. So in this question, this whole thing would be considered theta. So if I wanted this property, sine theta over theta, and I'm saying theta is 5x, I would like the denominator here to be 5x, because if I have sine 5x divided by 5x, that'll be this property right here. I'm going to be able to replace it with just the number 1. Well, what we do is, as x goes to 0, remember, don't touch the trig ratio, leave it alone. But this one, you're going to be able to make some mathematical adjustments to. Look at that. It's now sine theta over theta. These are the same. Now, with a fraction, if I had the fraction 2/5 and say, I'm going to multiply the bottom by 3, you can do that as long as you're going to multiply the numerator by the same thing. You can't multiply just the denominator without touching the numerator. So because I multiplied by 5 here, I'm also going to multiply by 5 up here. This bracket here is now this property that we have. It's the sine of theta over theta, as theta, the angle here, would be getting close to 0. So this is 5 from out here. This bracket, the big red bracket, is going to be just equal to a 1. Therefore, I know the answer is 5. So look at this one. Limit as x is approaching 0, and I've got 8x. Now I have sine 5x. So this is my theta. That means I want 5x here, not 8x. So what we're going to do is just kind of peel the 8 off to the front because it's just 8 times x. So 8 and the x separate out, that is still 8 times x. Sine 5x to the denominator. We're going to put a 5 here because now that'll give me theta over sine theta. If you multiply the numerator by 5, you have to multiply the denominator by 5. So what we end up having is 8/5 out front. This bracket is theta over sine of theta as the angle is going to 0. That gets replaced with a 1, giving me an answer of 8/5. Okay, let's look at a couple more trig ones. Now you've got to be careful. Don't get blinded and just plowing ahead without thinking things through. And I don't know how many would notice right away, but what happens is students just blindly say, oh, look at that theta over sine theta. They pull the 4 out, not noticing, wait a second, this isn't approaching 0. If it's not approaching 0, that property we're using does not apply. All you would do here is simply substitute pi over 4 wherever there's an x. Sine. Remember, that's always your first option, direct substitution. The only time you're in trouble is when direct substitution gives you 0 over 0. Well, here, this is going to give me pi. The sine of pi over 4, hopefully you can remember that from last semester, pi over 4 is 45. Your triangle that goes with that is 1, 1, root 2. The sine of 45 or pi over 4 is 1 over root 2. So that's going to get replaced with 1 over root 2. To take this and divide by a fraction, you just multiply by the reciprocal, and I would get pi multiplied by radical 2. That would be my answer. So notice I didn't get into that property at all because the angle wasn't approaching 0. Same thing here. Students look at this and say, oh yeah, there's that. I remember he showed us this property, but look at the difference. It is, x is going to 0, but this time it's not sine, it's cosine. Well, if it's cosine, the cosine of 0 isn't 0. The cosine of 0 is just 1. So I'm not going to get 0 on the bottom. It is going to be 6 times 0. X is going to 0. 3 times 0 is 0. But I can take the cosine of 0 and not get 0 in the denominator. So 6 times 0 is 0. Cosine of 0 is 1. You're allowed to divide by 1, no problem. Your answer would be 0. We'll jump over these ones. There's a couple more. I did examples similar to these already, so if you had to, you could kind of look back at them. But these ones here are a little bit more complicated. Let's take this one, for example. So now you've got an exponent on here. Well, what we're going to do is you'll notice that the exponent here and the exponent on the x are both 3's. Now, the 2 is not cubed. The mistake students make is they treat the top as if it were this. It is not that. It's only x cubed, not the 2 cubed. So the 2 is going to stay out here. However, the x and the sine of 3x are both raised to the third power. So I'm going to put them in a big bracket and just put a cubed on the outside. And then what I'm going to try and do is set up my property where I get theta over sine of theta. So looking here, this is theta, meaning I'd like to have 3x here. Done. All right, here's where your students will get caught. They'll say, oh, we did this earlier. You put 3 there, you put 3 there. Yes, that was right earlier, but earlier there was nothing out here on the exponent. When I put that 3 in there, it's actually going to get cubed, which means down here, I need to put 3 cubed to offset the 3 because it was inside the bracket of everything getting cubed, leaving me with 2 over 27. 3 cubed is 27. This is 1. That's your sine, or your theta over sine theta. Theta is going to 0. 1 to any power is still 1. So you got a 1 cubed. Your final answer would be 2 over 27. You jump over that one. I don't think that's one I'd worry about this semester. And I'll mention this one, and then I'll mention this one. And these are two of the more challenging ones. So yeah, you might run into them. And if you have to slow the video down, back it up, do so. In this one, you have to use trig identities from the end of pre-calc 12A. We did trig identities. And you have a trig identity that says the tangent of any angle is equal to the sine of that angle divided by the cosine of that angle. Again, trig identities that we're supposed to have brought with us from our prerequisite course 12A. Okay, so what I would do here is I would put that identity in for both the numerator and denominator, because everything we've done so far is related to sines and cosines. So I'm going to change tan 3x into sine 3x over cos 3x. That's another way to write, using your identity, tangent 3x. The denominator, which is tangent 5x, is going to be sine 5x over cosine 5x. Well, almost any time we've ever run into this, we don't like to have a fraction divided by a fraction. We're going to tidy this up and change its appearance a little bit here. So to divide by a fraction, you multiply by the reciprocal. So I'm going to go sine 3x divided by cos 3x. I'm going to multiply it by the reciprocal. So that'll be cos 5x over sine of 5x. And now we're going to try and set up our identity here. Remember, cosine of 0, we're not one bit afraid of that, because cosine of 0 is just equal to 1. So this term here and this term here are not causing us any grief whatsoever. If you have a bunch of things multiplied together, you can shuffle around the order you write them down. So I'm just going to shuffle around the order of things here, and I'm going to do this. So I'm going to leave my sine 3x there. I'm just going to leave it blank underneath it for now. I'm going to put my sine 5x on the bottom here, leave it. Okay, and then I'm going to take these two that I'm not too worried about, and I'm going to put them out at the end. That there. cos 3x. Now, this looks different than the line above, but it's the same thing. It's sine 3x times cos 5x. That's what I got here. And it's cos 3x multiplied by sine 5x, which is what I've got here. So I've just changed it around. And the reason I've done it is because I can put 0 in here, and the cosine of 0 will just be 1. The cosine of 0 will just be 1. So these are nothing more than 1s as I substitute 0. These are the ones that are problems because the sine of 0 is 0, and the sine of 0 here would also be 0, so it's 0 divided by 0. Well, we're going to use our identity twice. I want sine theta over theta. Done. There it is. Now I've put 3x in the denominator. There's no exponent here to worry about, which means I'm going to put 3x in the numerator. This one, I need to put 5x in the numerator because I want theta over sine theta. That means I need to put 5x in the denominator here. Okay, how does this all help us? Let's see what we've got now. So we've got our identity twice. This is sine theta over theta, theta going to 0. That's 1. Theta over sine theta, theta going to 0. That's 1. Cosine of 0, that's 1. Cosine of 0, that's 1. Now, if you say x is 0, you say, well, 3 times 0 is 0. Oh, it's no good. I still got 0 over 0. But this factor x will cross out this factor x, leaving you with a 3/5 at the end. So when you multiply that all through, we actually get an answer, 3 over 5. So there's where you use a trig identity when you run into tangent. So if you see tangent in a limit question, as x is going to 0, you're going to want to put in your, these are called your quotient identities, or your quotient identity. There's one for cotangent, which is just this flipped over. Again, stuff from last semester. All right, I got one more. I'm going to start on a clean page with this one. And all right, here we go. Well, this one starts to look more confusing because you've got a lot of exponents on the go here. They're pretty easy to pick out when you're going to use this strategy. You're going to have some trig, usually sine, some angle to an exponent. And then you'll have multiple terms down here. Well, these multiple terms will always have a common factor in them. And if you look here, the common factor between these two is x to the 4th. So you're going to start this one out with some factoring. Not going to touch the numerator, just leave it as it is. So you got sine to the 4th x over, take out your common factor, which is x to the 4th, leaving me with 2x minus 3. Well, the good news is what's usually going to happen is the common factor and the trig ratio are going to end up having the same exponent on them. If they don't, this method I'm going to show you doesn't work. So it's built around the fact that these have to turn out being the same. If they don't, again, something's either wrong or the question has some other strategy besides what you're trying. All right, like we did earlier with the one with exponents, we're going to group these two in a big bracket. We're going to put sine x and x down here. Now we're going to put a 4 here. Oh, sorry, there's a 3 in front of this, I forgot. Okay, so there's a 3 here. And blue. So that was in the original question. Sine 3x to the 4th power. Sine 3x to the 4th power. X is to the 4th power. X is to the 4th power. This 2x to the minus 3 is not to the 4th power, so it's going to stay out here by itself for now. Then we're going to try and set up that lone identity that I get you to work through. The limit of sine theta over theta as the angle goes to 0 is always equal to 1. So that's important. Theta in this question is 3x. I need to put a 3 there. Now this is one you got to be careful. The 3 I've put here is inside the big brackets where everything's to the 4th. So when I go to balance this out and say, well, I put a 3 in the bottom, you can't just put a 3 here because the 3 is to the 4th power. You need to put a 3 to the 4th there. Now it's 3 to the 4th, 3 to the 4th. Those two would essentially be equal to 1, which you're allowed to do. We've now got 1 to the 4th. 3 to the 4th is 81. X is going to 0, so that'd be 0 minus 3, leaving us with, so 1 to the 4th is 1, 81, divided by negative 3 Our answer would be negative 27. All right, so that is the end of what we're going to cover with limits. So that last section is just a quick overview of what we do when we have the limits approaching infinity, or if we throw trigonometric functions into the mixture. Um, I do have already practice in there on limits at infinity in your class notebooks, so you can find them under handouts. I'm going to dig out a few questions on limits of trig functions, and then we'll have a quick assignment, a couple of quick questions on that, and that will put us in place then to do a unit summary assignment early next week. All right.